Okay, so in this video, we'll be talking about the introduction or our introduction to integral calculus. Okay, so first we will have the definition of integral calculus. So what is an integral? So an integral is, in simple terms, is a mathematical object, no, that represents the area under a curve, no, and also it is defined as the reverse operation of differentiation. So integral itself is a reverse form of or the reverse operation of differentiation. So you cannot take integral calculus if you are not yet finished, no, or have an ample knowledge on differential calculus. Okay, so let's analyze the first definition of an integral. Okay, so for example, if we have a graph, no, okay, so let's create a graph here, our x and y axis. Okay, so let's just erase this one first. Okay, so if we're going to create a graph, okay, yeah. So for example, if we have a the exponential growth or the growth of a certain commodity, no? So for example, we have this one, okay. So if we are going to analyze, no, the area under this one with respect to the x-axis, so this area could be, for example, this is what we call as the increment, no? The increment length. So we call this one as the change of our x-axis. So this will be our dx, no? This x and this is y. And moreover, no? So we could have this one as the area. So we're going to get the area. So we have this one is a somewhat, if you're going to describe this one, this is the function of, for example, the function is equal to e to the x, no? If we're going to describe that one. So if we're going to get the area, no? So that will be this one, no? The area is equal to this length here times the change, no? Okay, change. So that would be ex dx. Now, because this is an accumulation, so by using integral, we could have found one as ex dx, covering the limit from here to this limit here. So we could have, for example, this is 0 and this is our a. So a coordinates, so a, b. So we could have that one as a 0. So this itself is an integral. The next is, by definition, is the reverse of integration or the reverse of differentiation. For example, you have the differential of x squared or derivative of x squared. So this will be 2x dx. So if we are going to integrate this one, so we will be going back to the function itself, which is equal to x squared. No, so there is the process of integrating is getting back the function in which we get from deriving that function. No, okay. Let's proceed. So we have the importance of integral. So the applications of integral. So they have vast applications in various fields such as physics, engineering, and economics. No, so like just what I did on the previous slide. So the example I gave it for the area is the area of a increase in commodity, the demand of commodity. So that is economics. Engineering. So if you are taking engineering, so integrals plays an important role, especially in fluids, fluid mechanics, and also in physics. The three laws of motion of Isaac Newton can be also described. If you're going to get the speed with respect to the acceleration or the distance with respect to the speed, it could be also we could also use integral to describe those equations. Then they help in calculating quantities accumulated over time. So just like what I said earlier, so integral could be used for calculating in terms of time, the distances traveled, the areas, volumes, and also in the understanding of the probabilities, the accumulated probabilities. Okay, so we have two fundamental theory of calculus, no? Each of those one represent, no, the connection between differential and integral calculus. So first, this theorem connects differentiation and integration, showing the R inverse operations. So for part one, so this is all about the integral. You know, states that if a function is continuous function with limits from the coordinates a and b, or b and a, so the new function is the antiderivative of that first function. So for example, we have this one. So this is our function, okay, f of x. So our limit, because our coordinate is a, b, so our limit is b to a, or if you have that one in terms of y-axis, so that's a to b, no? So dx, so the integral of that one, so to get the value of the integral, so we will only subtract the value of b, the value of the function in which we are going to substitute the value of x for b minus the value of the function substituted with the with the lower limit, which is a, no? So in which this one is a function, no, a function, a new function itself. Then part two of the theorem is also for the derivative. Now, if we're going to get if the antiderivative of the function, if we're going to get the derivative of that one, f, so that will be equal to the given function itself. For example, we have the integral of f of t, so that is in terms of x. So the if we're going to derive this one, so the value of this one, no, the value of the derivative of this one will be equal to the function, no, in which this function was being derived to get this f of. So that is the connection between integral and differential calculus. So they are just um, um, two reverse processes of itself. Okay. So to have more understanding, we'll have an illustrative example. Okay. So to understand the relationship, of these two, imagine you are driving a car. So the speed of the car, rate of change of the position can be taught as a derivative. So speed, or the change in rate of position. So this would be if our car, for example, we have here car here, no? So stroke car. Okay. So we have here our car. Okay. So this will be the road, no? So at time 0, so our s is equals to 0. So if we will travel going that one, so this will be at time t. So we have also here, let's just say our time is just time itself, no? T, let's just erase that one, no? Mhm. Okay, so let's see, this is T1, no? T1. So we have here our U, which is equal to S1. Okay, this point, no, to this point. So we could describe this one because it's exchange itself, no? Where's my pen? So this will be equal to ds dt, no? So we're going to get s, no? S itself. So we need to get the integral of this one with the limits from t1 0, no? From 0 to t1. So this is now the value, the total distance traveled, no? So to get the integral of the total distance traveled, so you must, to get the total distance traveled, so you must have the derivative of the speed, no? with the limits from with the limits is equal to time. Okay, so historical development. So the concept of integration has ancient origins, with the early methods of calculating areas and volume used by the Egyptians and Greeks, because the main purpose of the integral is to calculate the given area and the volume of solids, no? So because if you have regular shaped solids or areas, we could easily calculate the areas or volume, no, by using the usual formulas. But what if the given shape is irregular, no? So that is one of the main purpose of having integral calculus. Then the method of exhaustion used by Archimedes is a precursor to the concept of integral. So that the the method of exhaustion basically is, for example, if you have an irregular shape area, so you will divide or segment that that shape into shapes that are regular. So you are going to get data by parts until you will uh, you will be able to get the approximate. So that is approximation or approximate area of that given irregular solid. So that is also part of the discussion in integral calculus, which is all about the approximation, no approximation of integration. Okay, so there he comes Isaac Newton. So Isaac Newton, and which with his counterpart, I guess we could not say them as counterpart because they developed calculus separately. Isaac Newton was most credited for integral, while Gottfried Wilhelm Leibniz is um, credited for the differential, not knowing that the two concepts that they are doing is just the reverse of each other, forming differential integral calculus. So they developed that one on the same century, which is 17th century. Isaac Newton is, I believe he is in English, and Leibniz is, correct me if I'm wrong, you could have that on the comment. He is German. No? So um, Newton developed the idea of calculus through his work on physics and law of motion. And Leibniz developed here the systematic approach to calculus with clear notation that we use today. So basically, Newton developed calculus in order for him to grasp the other applications of the three laws of motion, similar to the problem on volumes and areas. So what if the the three laws of motions now uh, are described by, for example, um, the speed could be described by a trigonometric function, or what is polar coordinate if we're going to have that one. So that's why Isaac Newton developed such the calculus, So because he doesn't want to do approximation, also because the known purpose of the time, especially in solving the areas of irregular shapes, is approximation, So what Newton did is he incorporated analytic geometry, into solving the area, By doing so, he managed to create integral calculus. While Leibniz is the reason why we have now the notation for calculus. We have the dx/dt, the integral sign itself, and everything, that we are going to do or that we are going to follow, especially in getting the solution of any derivative or any integrals. Okay. So in 18th and 19th century, so further development and refinement of integral calculus with the contributions of mathematicians like Leonard Euler, Paul Friedrich Gauss, and Agustin Louis Cauchy. So the development of integral calculus, from doing getting the change of rate or the volumes and areas or describing the applications of Newton's law of motion became much refined until it is now transcends, not only the rules of motion but also on electrical engineering, the charges, on fluid mechanics, the flow of fluids, and even on advanced mathematics itself, So, if we're going to have an example of that, the foundation of Laplace transform, the Z transform, is integral itself, So that's why the creation of calculus, and the understanding of it was very impactful, to the development also of our understanding of mathematics, physics, and engineering. Okay, so I believe that will be all for this video. Thank you for watching, and as always, enjoy learning.